You are back with us. We are Cambridge University Astronomy, and we are back with our Wednesday evening of astronomy. As always, through this lockdown period, we're doing our Wednesday evenings remotely rather than in person. And so we have our normal format of a headline speaker followed by some observing. I've spoken to the Cambridge Astronomical Association. They tell me that the sky is looking reasonably clear, so we're going to get some stargazing in the second half. Before that, I'm very delighted to invite and to welcome our guest speaker. I'm here with Dr. Belinda Wilkes, who is the former director of NASA's Chandra X-ray Center, who's going to tell us all about viewing extragalactic sources with the sharp X-ray eyes of Chandra. Yes, with that, over to you, Belinda.
Okay, can you see that screen okay, Matt? Hopefully. Good evening, everybody. It's a real pleasure to be here with you on Zoom. Wish I could see some of you in person, but this is certainly better than not being with you at all. So I recently retired, actually only at the end of September, as the director of NASA's Chandra X-ray Center, which operates and provides the Science Center for NASA's Chandra X-ray Observatory. And it was really a wonderful job. I had worked with the observatory since right before launch, a couple of years before launch, which was in 1999 on the Shuttle Columbia. And the team is really incredible, very dedicated team, about 160 people who work at the Center for Astrophysics in Cambridge, Mass, operating and supporting the science community with their observations in the X-rays. So today I'm going to start out by showing you the launch, because it's always fun to see a shuttle launch, and showing you what the telescope looked like. This is a picture actually that we minted especially for the 20th anniversary in 2019, when we had a lot of extra events and celebratory things going on. And of course, it's unlikely to look like this now because it's been up there for 21 years now. It turned 21 this past summer. Slide, which puts Chandra into the shows where Chandra belongs in terms of NASA's great observatories, which cover up all the way across the electromagnetic spectrum, or did, from the infrared to the gamma ray. And below I have a temperature scale and a wavelength scale, showing that in the gamma rays on the far left, for a thermal emission to give you gamma rays, it has to be at 10 billion degrees, billion in the US, sorry, so 1,000 million. And in the X-rays, 10 million degrees, etc. So the Fermi Gamma Ray Telescope is currently operating in the gamma rays. The one that was originally called the Great Observatory was the Compton Gamma Ray Observatory, which actually deorbited quite a number of years ago now and landed in the Southern Atlantic or the Southern Pacific, I forget exactly which. But Fermi is doing a wonderful job looking at the gamma rays, and we do quite a lot of work with them. Chandra, as you know now, is an X-ray telescope. And then there's the Hubble Space Telescope, which everybody seems to know. And I always jokingly say that the reason for that is because they had a problem at the beginning. So they really had to sell themselves to get the money to fix it. Basically, they needed glasses. They needed to put lenses in front of the mirrors because they had not been figured correctly. They've been working now for almost 30 years, and they take beautiful pictures. And again, we do a lot of work with them, looking at the same sources in the optical and UV and in the X-ray to understand how they work. And then the fourth one is the Spitzer Space Telescope, which stopped operating not very long ago now, and it observed in the infrared. And again, we worked with them quite a lot to observe the same sources in the infrared and the X-ray. And the infrared is the longer wavelength and much cooler, so only 100 Kelvin to give you infrared. So this fleet was able to look at celestial sources across the electromagnetic spectrum and understand them much better than they would if they only had data in one or two of these bands. Now this is the shuttle on the 23rd of July 1999, which took off from Cape Canaveral in Florida. You can see the engines firing here, and then the shuttle will raise up. I was there at the launch, about 3 or 4 miles away, And if any of you have ever been to a launch, you'll know what I mean when I say it's a really incredible experience. This was at night, so the whole sky lit up like it was day, and the ground under your feet, even several miles away, just shakes. So it gives you some understanding of how much power it takes to escape from the Earth's gravity, which you need to do, any rocket needs to do to get up into space to orbit the Earth or go beyond. And also just that the human race can do these things. So it really was an amazing experience. The first thing that the shuttle crew did when they got up into orbit was let Chandra go. So this is our mission specialist, Katie Coleman, taking a picture as they let Chandra go out of the bay. They opened the bay, let it go, and then they backed away very, very carefully because it had a lot of fuel, still does actually, a lot of fuel on board. And if anything had gone wrong, everybody would have been blown up. But it all went very smoothly, so they're just gradually backing away from Chandra. And I'm going to let it go because it turns at an angle and you'll be able to see the telescope on its side in a few minutes. Not a few minutes, a few seconds. It's actually as big as a US school bus, one of those yellow school buses you see on all the movies. Very big. It's the biggest payload that any shuttle ever took up into space. So there is a telescope without the solar arrays panels outside, and on the back is its own rocket to get it into its high Earth orbit. And this slide shows the orbit. On the right, I'm showing the lunar orbit, is the large circle. The Earth is in the middle, in the red is the radiation zones. And then you can see Chandra's orbit. It goes about a third of the way to the moon, takes 3 days to go around. So it's a lot further up than the Hubble Space Telescope, which is in the shuttle orbit, which is about an hour and a half long. So much, much closer to the Earth. And then on the left, we see just the Chandra orbit and how it comes into the radiation zones and goes out again. It moves much more quickly when it's near the Earth, of course. So it's outside of the radiation zones and can observe for 70% of the time during this 3-day period. And that is actually a much higher efficiency on the sky of observing than you can get in low Earth orbit. So that's where Chandra is. It's still there. Its orbit does precess a bit, but it's stayed at 3 days very closely over 21 years now. So how do we focus light in the X-rays? Some of you will know this, others may not. If you think about a visible light mirror, or a visible light telescope, what I'm showing here is a light ray coming in from, or light rays coming in from a source at infinity. So they come in as parallel light. They're hitting a mirror on the right-hand end, which reflects them down to a focus point, which is the red X. And this is what we're used to doing. If we look at ourselves in the mirror, the light bounces directly off the mirror back at us at 90 degrees. And that's how we see our image. That doesn't work in the X-rays. X-rays just go right through something like a mirror. They don't even notice it's there. So how do we focus them? We have to do it by grazing incidence. And what I'm showing you here is the little green, either green or black, I can't tell, but the lines there are actually the cross section of a cylindrical mirror, with 2 cylindrical mirrors. And again, the X-rays are coming in from the left, parallel light, and they hit the edge at about 1 to 2 degrees. Grazing incidence on this mirror, there's 2 of them. Each X-ray photon hits a paraboloid, then a hyperboloid, and then focuses down at the focal point, which is actually 10 meters away from the telescopes, from the mirrors themselves. And we have 4 sets of nested mirrors so that we can cover a wide X-ray energy range. So these are the smoothest mirrors that have ever been made, because X-rays have very short wavelength, and if you have any sort of blemish coming in at grazing incidence at very short wavelengths, then the light will not make a good focus. Chandra has the best focus of any X-ray telescope ever. It has a resolution of about half an arc-second, and that matches ground-based telescopes on a very good night when the seeing is very steady. There's not too much motion of your images in the atmosphere. So this was the first time, only time. There's no other mission, X-ray mission, that can focus this well, either that has ever flown or is yet in the planning stages. So we're hoping to work towards one. So this is a cross-section of Chandra itself, showing that in orange, the X-rays coming in. And you can see in blue, the sort of cross-section of these cylindrical mirrors that is cut away, so you can see the light going through. And then the detectors are at the far lower right. So we have an X-ray telescope. What are we going to do with it? What gives you X-rays, and why do we want to look at them? Well, X-rays come from the hottest and most violent, and I might argue the most exciting places in the universe. Here are some examples. Stars. Well, our sun doesn't give us very many X-rays. We actually can see X-rays from our sun because it's so nearby, but stars are only bright X-ray sources at violent times in their life. So when they're being born, if they're interacting, so binary systems that get too close and tend to interact with one another, merging binaries, and stars that are dying. So supernova remnants, for example, when a massive star blows up. Black holes of all sizes. They've got a lot of gravity, so they tend to pull in material from around them, and that material gets very hot, and you get X-rays as part of that. So these are active black holes. Galaxies contain a lot of very hot gas that you wouldn't be able to see unless you could look in the X-rays. But also planets. We actually see Xray Aurora on Jupiter, and this is an optical picture of Jupiter showing the North Pole on the left and the South Pole on the right, and the purple is the X-ray emission. These are aurorae very similar to the aurorae we see on the Earth, but higher energy. I don't think there are many X-rays from ours, though I'm not an expert on this part of science. So basically, most types of celestial sources do give us X-rays, certainly at certain times of their lives. I'm going to illustrate the big step forward that Chandra took by showing you a picture from the previously highest resolution X-ray telescope, Rosat, which was a UK, US, German collaboration that flew in the early 90s. And this is the Orion Nebula in X-rays looked at with Rosat. And it had 250 sources that we could count. And you can see very clearly in the middle, everything is merged together. There's too many stars there, we can't resolve them. And all we see is a big blob. And then the brightest 3 stars in the middle could be measured. Now I'm going to merge into the Chandra field. And now you see 14,000 X-ray sources, all young hot stars. These are very unstable and violent places. As the gas and dust around them falls in due to gravity, gets hot, you have a star that's starting to form, it blows material away, and there's a lot of X-ray emission coming from these. You can see now all the way down into the middle, and these bright stars look big just because they're bright. They're not any bigger physically than the others. And you can also see small dots around in the wings of those bright stars. So you can resolve all the neighbors to those stars as well. So it really makes a huge difference having good spatial resolution. And Chandra has turned into to be a very good young star finder. And now adding the optical HST picture of this region, you can see all the gas and the dust now that's sitting in the way. And it's actually quite hard to see all these stars in the optical. A lot of them get hidden by the dust, but if they're X-ray sources, the X-rays that shine all the way through. So we can find all the youngest stars by looking at these star-forming regions, like the Orion Nebula in the X-rays. The Orion Nebula, by the way, you probably all know better than me, is in the middle of Orion's Dagger. It's also called a sword. I think the sword is the American terminology and the dagger is here, but or maybe the other way around. So you can see it with your naked eye on a good clear night. Okay, today though, I'm mostly going to talk about extragalactic science. And my first topic is supermassive black holes in the nuclei of active galaxies. Every galaxy has a supermassive black hole in its center, at least we believe. Every time we've looked, we've found one. Our Milky Way has one, but it's not very big and it's pretty quiet. The ones that are active means that the supermassive black hole has a lot of material around it. That material is trying to fall in due to gravity, and it gets very hot in doing so because there's a lot of other material in the way. It rubs against the other material and gets hot. So what I'm showing you on the right is the geometry of the central part of a galaxy with a supermassive black hole in the core, which can be anywhere from 1 million to 10 billion times the mass of our sun. So extremely big. in terms of mass, but very small in terms of size. And this accretion disk around actually cuts off the light at its edge on. But if you were looking down from the top, you'd see this incredibly bright source in the center that really outshines even the galaxy it's sitting in. These sources also have jets from the poles of the accretion disk, they come from very close to the black hole, and I'll be talking about those soon as well. Radio loud quasars look like the one on the left in the radio. So they have these beautiful structures. The quasar is the white dot in the middle. They have a jet. You can see a jet coming out from the right-hand side. And then this is plasma streaming along magnetic fields. Eventually, it interacts with material around it, slows down, and you get these beautiful lobes with hot spots in them. And I'm going to be showing you some of those. So I'd like to tell you the story of the first targeted source, which was a quasar, similar to Cygnus A, which I just showed you, but further away, so that all you should see, even in the X-rays, is a point source on which you can focus your telescope. That's why we were looking at it. It's a redshift of 1/2, which is 9 gigayears away. However, when we looked at it, this is what we saw. On the left, you see the point source with some wings around it, but it's a point source. You can focus on it, and it still is a point source. However, on the right, you see this linear structure. This is extending to the west, about 9 arc seconds long, which is 250,000 light years at this redshift. And to begin with, it had the engineers and the astronomers in the control center actually quite worried. They were trying to figure out if there was something in the telescope that could have caused this light to be reflected off in the wrong direction. But no one could explain how you'd get this lovely linear structure. And then it turned out somebody remembered that this is a radio loud quasar, so supermassive black hole with radio jets. Parkes is a radio telescope in Australia, and that's what it's named for, the PKS. And it has a radio jet, and this X-ray jet lies right on top of the radio jet. So here I'm going to show contour plots of the radio at the bottom and the X-ray at the top. The radio telescope resolution is much higher than that of the Chandra X-ray telescope. They have interferometers and can resolve structures that are very, very small. So you can see the jet going off. It has some structure in it, some hot spots, and the X-ray jet lies right on top of it. Notice that the radio jet seems to bend at some point. What we think is that there's a big clump of cold material. The plasma drives into the cold material, and the cold material slows it down and deflects it off to the north. And there are no X-rays that get deflected off. So we think that what's happening is that the plasma slows down enough that we no longer get X-ray emission from it, but we are still getting the lower energy radio. So this started a whole new industry in astronomy of studying radio jets, which we had known for many years, decades, but didn't know a huge amount about because we only really could observe them in the radio. And we now observe them in the X-ray as well. And putting that data together, we've learned a lot more about how jets work. Here's another one. This is actually a nearby source, Messier 87. It's a supermassive black hole in the middle of a cluster of galaxies. And you can see a jet down in the core there with the box around it. And then there's a lot of hot gas around because it's in the middle of clusters. And I'll be showing you some more clusters later. If we zoom in on that jet, you can see that it has a core on the left, and then just going up slightly to the right, there's a jet feature with some hot spots in it, some bright spots. And then if we zoom in on the jet, at the bottom we have the Chandra picture. On the left is a supermassive black hole, a very bright point source. Above that is the Hubble Space Telescope picture. So we're getting optical light also from this jet. And at the top is the radio image from the Very Large Array in New Mexico. So you can see the structure in the jets at all these wavelengths, but they actually look somewhat different. Some similarities, some differences. So for each of these hotspots, you can look at for example, the relative amount of optical to radio to X-ray emission and learn about the physical conditions and the magnetic fields in that jet. And we've also seen superluminal motion of these spots. We've seen them change in the X-ray and the radio and with Hubble. Over the lifetime of Chandra, and earlier than that as well, before Chandra came along. So we've learned a lot about jets from combining these types of data. I'd also can't resist zooming in on the supermassive black hole in the center of M87. Some of you may remember that this is now very famous. is the first ever image of a horizon of a black hole. That was obtained by the Vendorizing Telescope, which is a radio telescope made up of lots of telescopes all over the globe, and basically uses the motion of the Earth to create a huge dish that can then have very, very high resolution. The resolution is determined by the distance between the most distant telescopes. So if we make them as far apart as the diameter of the Earth, you get very high resolution. This is 40 micro-arcseconds across, 50,000 times better resolution than Chandra has. So there's no way we would see this kind of structure with Chandra, but we are actually seeing X-rays from very close to here. We know they come from very close to the horizon of the supermassive black hole. Okay, moving on to a somewhat different topic, still supermassive black holes, but binary ones. I mentioned binary stars that move around one another, rather like the Earth-Moon system, though of course the Earth and the Moon are not quite the same kinds of sources. But imagine another star being near our sun and they move around one another. Supermassive black holes do the same thing in the centers of galaxies. We end up with sometimes two of them. And this is usually because we've got galaxies that are merging together. They've got too close. They can't escape from one another. And each one had a supermassive black hole in its core. And both of those supermassive black holes were accreting materials, so they're strong X-ray sources. And we're finding quite a few more of these with Chandra because Chandra can often resolve them. So this is NGC 6240. The red and yellow is the optical emission. And instead of being a nice, beautiful structure like the spiral galaxy, our Milky Way, or the Andromeda galaxy, here, this looks like a mess. There are two galaxies that have come together and they're all coming at different angles, and it basically has not settled down yet. They can't get away from each other, but everything is in great turbulence. But in the X-ray, the blue is showing us two supermassive black holes, two bright X-ray sources, which are supermassive black holes with accretion disks around them that are giving us a lot of X-ray light. This is binary black holes is quite a hot topic in the last few years because of the LIGO gravitational wave telescope. LIGO and Virgo have been finding stellar mass black holes that are binary stellar mass black holes that merge and give strong gravitational wave signals. These are supermassive black holes. They're at least 1 million times bigger excuse me, than a stellar mass black hole. And LIGO would not be able to see the waves from this. We need a much bigger telescope. And ESA has one planned that will be launching in the 2030s called LISA, and that will put detectors in space, so it can have much bigger separations than the ones on the surface of the Earth, and they will be able to detect gravitational waves from merging supermassive black holes. This is a movie put together by our very talented public outreach group at the Chandra X-ray Center, showing you what happened to these two galaxies. So we had spiral galaxies coming together. Now we've zoomed in on the core and we see these two little orange disks, which are accretion disks giving us the light, with little black centers, which you probably can't tell are there, but they are. And so they're orbiting one another, and gradually, as time goes by, probably millions of years, they slow one another down and they will eventually merge. And so that's what we're seeing here. And when they do, they create gravitational waves, which are being shown in blue here. And so LISA hopefully will see some of these, not from this source because they're too far apart in this source, but hopefully we'll see some of these once it gets going in about 20 years time, 15 or 20 years time. We found more. Here's another couple of examples. Again, the Chandra data is in blue and white, and the yellow on the left and red on the right is the optical emission from these merging galaxies that again look like a mess. They're not nice, tidy elliptical galaxies or spiral galaxies like we like to take our pictures of. But these are binary supermassive black holes in their centers as the galaxies merge. We also recently found a triple system. This is the only one I know of so far. This one is at a distance from us of 1 billion light years, and the black hole separations are less than 30,000 light years. And the X-ray picture is at the bottom, and you can see 3 point sources there, maybe with some X-ray extended emission around them. And then the optical picture is the one to the upper right. And again, you see 3 bright spots. To know they're all accreting supermassive black holes, you need to see the X-rays. It could otherwise just be a central star. cluster. So the X-rays confirm that this is 3 AGN, 3 active galaxies, which means supermassive black hole that's accreting. And these will actually merge much more quickly because they all interact with one another. So there are 3 times as many interactions going on. So they will slow down faster. Okay, I'd like to move to another topic now, that of clusters of galaxies. These are somewhat nearer than most of the supermassive black hole and what we call active galaxies that I've been showing you. But galaxies like to stay together. So we have our local group, the Milky Way, Andromeda, the Magellanic Clouds, and a few other little galaxies. That's called a group of galaxies because gravity pulls them together. Clusters of galaxies are actually the largest gravitationally bound systems in the universe, and they can have anywhere from 50 to thousands of galaxies that are basically can't escape from one another because of the gravity that is part of the cluster. This is the center, the optical picture of the center of the Perseus cluster, which is one nearby to us. And this sort of pink and purple spiry looking thing is what's called the brightest cluster galaxy. It's called NGC 1275. It's got beautiful filaments of star formation. And all those white things are galaxies. I'm now merging into the X-ray emitting hot gas in this cluster. You can see most of the galaxies disappear. They're not hot enough to give us X-rays. A few of them are. But in general, we see a huge amount of hot gas. We see 10 times as much mass in hot gas as there is in the galaxies. And so that partially explains how come there's so much gravity to hold everything together. We expected, since clusters of galaxies are very, very big, they've been around for a long time, that they'd be pretty boring, that we'd see lots of X-ray gas, we'd be able to measure its temperature, the temperature gradient, the amount of gas we saw, but we didn't expect anything like this structure that you're seeing here. And in fact, they all look like this. They all have this incredible structure. So what we're seeing is edges. The biggest one on the right going through the middle here is a cold front, very like the cold fronts we get in our own atmosphere, which is a pressure gradient. So you get a sharp edge here. And then in the core, right over NGC 1275, which is in the middle of this funny mouth-like structure, it almost looks like a couple of fishes' mouths in the center. These are actually voids where the radio jet, we've been talking about radio jets already. This is a supermassive black hole in the middle of NGC 1275, and it is sending out radio jets from that supermassive black hole, and that pushes away the hot X-ray gas. So you end up with a void which is filled with radio emission, and then shocks and sharp edges to the X-ray gas around that void. So there are several actually. There's 2 near the middle, there's one to the northwest here, and there's one to the south, and actually probably a few more further out. So it actually gives us a fossil record of all the jet activity there's been in this cluster of galaxies since it formed. And this little movie, again from our outreach people, just illustrates what I meant when I was waving my hands. The black hole sends out jets of plasma along magnetic fields, and it goes out into the X-ray gas, which is red in this particular movie, pushes it out of the way, heats it up some, and creates these voids, which are full of radio-emitting plasma. And here's an example where you can really see the whole thing, whereas in Perseus, because it's so nearby, you don't see it all at once. This is further away. It has a telephone number type name here, 2.6 billion light years away. Now the X-ray gas is in blue in this particular picture. The galaxies are in white. There's this brightest cluster galaxy is the biggest oval shape right in the middle. And the red is the radio jet, which you can see at some point during its lifetime changed direction, but it's filling the voids. And if you look carefully, you can become observers. You see there isn't much blue emission immediately next to that red emission. So the radio jet has made this void. What we think is happening here is the hot X-ray emitting gas, which dominates, as I mentioned, the normal matter in clusters, is a site of star formation. As the gas cools, stars can form. It also falls into the center due to gravity and accretes onto the central active nucleus and creates this bright source in the middle and these radio jets. The radio jets just come out and they push the hot gas aside and heat it up. And so that slows down both the star formation and the cooling of the gas falling into the middle. So it basically regulates the formation of stars in this region and slows down the growth of the black hole as well. It's what we call a feedback loop, which moderates the growth. And feedback loop is the sort of thing that a thermostat in your house has. You want it to be a certain temperature on your room. When it gets a little cooler, the thermostat turns on the heating comes in, the room warms up, and when it gets a little above where you want it to be, the heating turns off and it cools down again. So it's exactly the same thing that's happening, only on a huge scale and over a long time period. This is actually the largest continuous jet we've observed. It's more than a million light years from one end to the other. Okay, I'm just wondering if I have time now to do my last topic. I'll just quickly go through it. As well as hot X-ray gas in clusters of galaxies, we have what's called dark matter. I'm sure many of you have heard of it. In astronomy, we tend to call things by names that you understand. It's matter, it has gravity, but we can't see it until it's dark. We don't really know what it is yet. We put some limits on it. But clusters are a great place to study dark matter. There's actually 10 times as much dark matter as there is hot X-ray gas. And there's 10 times as much, this is roughly 10 times as much hot X-ray gas as there is galaxy mass. So here, in this picture, which is a merging set of clusters called the bullet cluster, the red is the hot X-ray gas. The white are the galaxies from Magellan observations, and then the dark matter is in purple, and we're measuring it via gravitational lensing. There's so much material there that the gravity lenses background sources, and you see them change shape, and you can work out how much dark matter is there. What we're seeing here is that the hot X-ray gas, when these two clusters move through each other, and I'm showing it, I'm moving on the next one. This is the gas and the dark matter. The clusters move through each other, and as they do that, the hot X-ray gas interacts with other gas particles going the other way and slows down. Just like if you blow smoke into the air, it'll slow down. However, if you shoot a bullet through the air, it goes a lot further because it's very dense and it's hard to stop it unless you put a target in the way. So these galaxies mostly just don't see one another. They keep going. And so here they are further beyond the X-ray gas. Now the dark matter has done the same thing. Even though we think it fills all that space, unlike the galaxies, which have space between them, those particles do not interact with one another. So that actually has cut down on the types of particle that can make up dark matter by putting limits on their self-interaction. And we've now observed a number of other clusters in a similar way. Okay, that's it for science, because my half hour is up. I'm just going to end with pictures of who we call our astronauts, because we have stayed in touch with them. They really love the fact that they launched this telescope that's still observing and making beautiful pictures 21 years later. This is a picture of the 5 of them on orbit, with a flag behind it with a picture of Chandra, which we now have in our hallway at the CXC. The shuttle launch made history not just because of X-ray astronomy, but because it had the first female commander. In the lower left is Eileen Collins. You can tell they're up in the shuttle, by the way, because their hair is all sticking up. So Eileen Collins is in the lower left. She was the commander. In the upper right is Katie Coleman, who was the Chandra mission specialist. And then in the upper left, Steve Hawley was originally, and actually is now again, an astrophysicist. He also went up on a couple of the Hubble Space Telescope shuttle missions. And then we have the pilot, Jeff Ashby, and an ESA astronaut, Michelle Tomini, who's the one at the bottom right. They come back and visit us, and this was in 2014, just after I became director. They came back for the 15 years of Chandra science. Only 4 of them were able to make it, so that's Steve and Michelle and Eileen and Katie. And here's a picture with me to prove that I was there too. And then last December, we had a 20 years of Chandra science, and 3 of them came back this time, and the 3 of them can make it. And here I am introducing them, and then they had a panel. They showed us a movie and talked us through some of the terrible things that happened on this launch of the shuttle that took Chandra up. And it's amazing, even just watching it, knowing that Chandra's been up safely operating for 21 years. We were going, phew, sort of amazed that it actually got up there. They had a series of things that went wrong, but everybody was very calm and worked through it, and it got there. It actually ended up being about 8 miles low, a few miles lower than it should have been. So to get to the final orbit, the people in the Operations Control Center back in Cambridge, Massachusetts, had to recalculate all the firings of the rocket engines to get it to the same final orbit, because they were starting from a different place. But they know how to do these things. They're professionals at launching things. So that was one of the things that went wrong. Anyway, so that's, I think, the end of my slides, except this is a montage of Chandra pictures, at least one of which you saw during my talk. So thank you very much. I'd be very happy to take questions.
Wonderful. Dr. Wilkes, thank you so much for that. That's absolutely fascinating. There have been a couple of questions coming through on YouTube. You can't ask questions as fast as you can in real time. So yes, if you do have any more questions for Dr. Wilkes, please put them in the YouTube chat. In the meantime, there's a question from Timothy, who is aged 8, who asks, how many black holes are there in space and what are they called?
What are they called? They tend to be called by their galaxy names, but every galaxy has a supermassive black hole, and there are billions of galaxies out there. And then a lot of stars end up being supermassive black holes, or neutron stars, which are the sort of step before, when stars blow up. So there are billions and billions. I couldn't actually give you an exact number. They tend to be called, as I mentioned, by the galaxy that they're in. So maybe 87, one I showed you, is the name of that galaxy. It's a Messier, number 87, sorry. It was in the Messier catalogue of galaxies that an astronomer called Messier found many years ago, and didn't at the time realize there was a supermassive black hole in the core. If they're stars, then often they're actually called by their constellation. So the brightest star in the Lyrae constellation, for example, is called Alpha Lyrae. I don't think that has a black hole in it, but if it was, the black hole would just be part of that system.
Wonderful, thank you. Just to give people a bit of time, but before your talk, we were chatting a bit about the future of X-ray astronomy. Do you mind talking a bit about what lies ahead for X-ray astronomy? Because obviously you can't do X-ray astronomy from the ground, right? So it's a very expensive business. You have to go to space. So yes. What can we expect in the coming years?
Yes. Well, Chandra, we hope will go for at least another decade. We have a contract with NASA to do that, assuming that it can keep operating and nothing major goes wrong. As I mentioned before, it's the only one with this high spatial resolution. So there's a group of people at the Chandra X-ray Center and also at the Center for Astrophysics who are working on a Chandra successor mission, which would be called LINX. It would be a larger mirror. It has to be different technology because our mirrors are very heavy. And when you go into space, the weight is very important because the heavier it is, the more it costs to take it up into space. So they're developing lightweight mirrors that can nest similarly, but in many, many shells of these mirrors. And that is actually going up at the moment, being assessed by the decadal survey that is run every decade on astronomy. And we're hoping, fingers crossed, that LINX will be the next big mission, sort of greater observatory that NASA will fly. But there are 4 that are vying for that position, so fingers are crossed. ESA has a new X-ray observatory that will go up in the early 2030s. It's called Athena, and it will have a much bigger mirror than Chandra has. Again, these lightweight nested mirrors, but the resolution will be about an order of magnitude worse. So about 5 to 10 arc seconds as opposed to half an arc second. So it'll be able to do a lot, but it won't be able to resolve, for example, these binary black holes in the middle of galaxies unless they're quite far apart. So there is a future. There are also some smaller missions that are being planned that are going up sooner, but none of them will have the spatial resolution that Chandra has.
Wonderful. Thank you so much. Yes, there are people coming on YouTube and saying that the talk was wonderful and they enjoyed it very much. I want a question from David Gwynn coming in. How did you get to be the director of the prestigious Chandra Telescope? What's the career path to such an illustrious role?
Well, I started out as a graduate student. I've been in the States for a long time. I should say postgraduate, doing my PhD here at the Institute of Astronomy, actually, many years ago. Then I went to Tucson, Arizona. In those days, I did optical astronomy. So So I went to Tucson, Arizona. I used the telescopes there at Kip Peak and at the University of Arizona for a couple of years as a postdoctoral fellow. Then I was offered a job at the Center for Astrophysics in the High Energy Astrophysics Division, which is basically X-ray division. And at that time, the Einstein Observatory had just, which was another NASA mission, had just finished operating. And we went from there to Rosat and then on to Chandra. And so I just was there for a long time, running different missions. I joined Chandra a couple of years before launch in the user support group. And then after a few years, we formed the director's office because we realized that the director needed help to run the observatory. He couldn't do it all on his own, and I was leading that. And so when the founding director decided to retire, I actually hadn't ever dreamt of being director, but I realized that if somebody came in from outside, I'd have to train them how to be director. So it would be much easier if I could be director myself. So I decided to apply, and it was a big international search, and I got the position. And it's really been a privilege and an honor to lead this incredible team, to be able to come and talk to you about all the wonderful science that we're doing. I used to do that before I was director as well, but now, of course, I have an even bigger role doing that, or had. So it really was a pleasure and a privilege and a wonderful job to have. And the team is so dedicated. They give so much time and effort to make sure that Chandra can do all its observing to the best of its ability. It's a great team to lead.
Thank you.
Now I'm just retired, and the next director is actually somebody who was working for me, another internal person, and he's already doing a great job in his first month. So it's good.
A question from Dave Allen, who wants to know, can Chandra help predict supernovae at all? Is that a thing Chandra can do?
Supernovae are not very easy to predict. We certainly look at them. We have what's called targets of opportunity, which can either be come in as a program that a peer review decides, if a certain supernova goes off, this person can look at it. Or is what we call director's discretionary time, which basically comes to me as a director. And I have a small team of people who will assess the requests for time that just come in and say, can we look at this supernova in the next few days because it just went off. They're usually found in the optical first. Often we can get a position better than, if they're not found in the optical, we can often get a position better than any other X-ray telescope. So we don't predict them. Basically, we react when they go off, and that's a general astronomical. It's the way supernovae are found. We react when they go off. Often it's the amateur astronomers who find them because they know the sky so much better than we do, and they sit and stare at it through their telescopes, which are very professional nowadays, and they'll let us know when a supernova goes off, and then all the professional telescopes will turn and look at it.
Excellent. Well, thank you very much, Dr. Wilkes. Absolutely fascinating talk. We'll have to pretend to have a virtual round of applause. I'm sure everyone is applauding at home. Very nice segue into the second half of the evening, mentioning the amateur astronomers. We have our dedicated team of amateur observers on call, and I think if the skies are as clear as they were about half an hour ago, then we should be able to switch over to you guys and do some observing.
Yeah, hi, good evening, Matt. Can you hear me okay?
I can hear you wonderfully, Paul. How are you doing?
Splendid. I'm talking here from the observatory in the dark. We were just having a firework display next door, which was making some very loud bangs and filling the sky with fireworks. But they seem to have taken a pause, so we'll get on and do some observing for you before they start up again. I'm here with my 14-inch telescope, and I've got my ordinary Canon camera connected to the back of it. And I'm going to show you straight away the target that I've managed to find first, and Brian is going to tell you about it, but he's going to curse me because it's not one of the ones that's on his list. But,
thank you, Paul.
Yeah, sorry, Brian.
Okay, which one is it?
You'll recognize it, don't worry.
Okay, good.
Name that nebula.
Yes, I will. The Ring Nebula. It's a glorious sight in a small telescope. And you can see there, it's a star that has ended its life. Not a large star, a dwarf star similar to the sun. Any star that's under 8 solar masses, when it runs out of nuclear fuel, it swells up into a giant and then it puffs off its outer layers and makes these often very beautiful planetary nebulae. And the word planetary nebulae is totally misleading. It was introduced by William Herschel, and what we're going to do tonight is we've got a little bit of a theme about William Herschel, who was a German musician who came to this country in 1757 when he was just 19. But he didn't start to become an astronomer until he was 35. But he went absolutely berserk. He would spend every clear night at the telescope, and during the daytime he made telescopes, and he would spend up to 16 hours a day making telescopes. So once he made many discoveries, including discovering the planet Uranus, and he's discovered over 2,500 nebulae and galaxies. And we'll look at some of them tonight. But this is a nice planetary nebula, which is in the constellation of Lyra. And it's about a light year away, a light year across. But the trouble with planetary nebulae are that very difficult to work out their distance and how old they are. And while books and websites give you ages and distances, you can take them with a pinch of salt. And if you look very closely, you can see there's a central star, and that's, well, not in this one, I can't quite see it.
No, me neither, Brian.
No, but if we have a larger scale telescope or a larger image, you would see it. But we're going to see another planetary nebula later in the show, and you will be able to see the white dwarf, and that's the remnant of the star that has puffed off its outer layers. Okie doke, we're ready to go to Mick. Have you got yours working?
Yes, I have now. I can.
Right, I will hand over to Mick while I go and find you the Vale Nebula, Brian.
Thank you. Okay, we're going to zoom over to Swaffham Prior, where Mick is. And what's your first object?
Mars.
Mars, good. We looked at Mars the last couple of weeks, and because
Can
Mars...
we see it?
Yes, we've got it.
Good. Okay. That's right. I've had a lot of problems, but I managed to get Mars.
No, that's okay. And is South at the top? Have you flipped it over? No, it's not. If you could flip it over, I'll be a happy bunny.
Okay. Let me just...
Right. Because last week we looked at it the other way up. Astronomical telescopes always give an upside down image. So south is at the top. At the moment, we've got north at the top. So Mick will flip the Mars the other way up. Here we come. Any second.
Here somewhere. There we are.
There we go. That's it. Now,
there we go.
If we look at the blob in the middle, if you remember last week, it was over to the one side, but Mars orbits orbital period takes just over 40 minutes longer than the Earth's rotational period. And so night after night, you see more or less the same face of Mars. It's more or less in step, but gradually the markings move further to the right. Now, you remember that that dark blob was called Syrtis Major, and that's a huge volcanic region. It's a very old region, over 3.5 billion years old. And its dark colour is due to the volcanic basaltic rock. And it isn't covered by any of the red dust that we see elsewhere in Mars. And above it is a slightly light patch, if you can point to it, just down, whoops, down a bit, that's it, just above there, that's it. That lighter patch just above the Syrtis Major is the Hellas Basin, which is a huge impact basin that fell about 4 billion years ago, or the asteroid that hit it was about 100 kilometers in diameter and made this huge impact basin. It's the largest impact site in the one of the largest impact sites in the solar system, and it's obviously heavily eroded and you can't see the crater anymore, but it's just a huge depression, over 2,000 kilometers wide and over 7 kilometers deep. Now, as you can see, the Syrtis Major looks a lot like Africa. And if we look at where South Africa is, especially where Cape Town is, on the south, on the southwest coastline of Africa, if you like, and that's where the Jezero crater is, where Perseverance rover is going to land, and that will be in February. It's on its way to Mars now. And then to the left of Syrtis Major, you can see a diagonal stripe going slightly upwards. That's it. Yeah, that's it. That's the Terra Cimmeria, which is named after the ancient Thracian seafaring people. And this is a dark area of highlands. It's covered with impact craters and water-carved valleys and sand and dust. And it's just below that, that dark area that the other lander that's very similar to Perseverance that has been on Mars since 2012, and that's Curiosity, and that's just below it. And not far from Curiosity's site is a crater, which we obviously can't see, called Herschel. And it's one of the largest craters on Mars. And it's the unusual crater because it's named after two people, William Herschel, who we're covering tonight, and his son, John Herschel. So all other craters on the moon and elsewhere in the solar system are all named after just one person. But this one crater's named after two. It's about 300 kilometers across. So that's Mars. And now we'll head over to Halton, where David should have something lined up for us. If you can hand over to David.
Hello.
Is it clear your way?
Yes.
Good. What have you got for us?
Let me have a look.
That will be...
Talking of Kurt Herschel's?
Yes, here we are. And this is the Caroline's Rose Cluster. Now, William Herschel, when he came over and started observing, his sister, Caroline, came over to assist him. And she helped him enormously. But in the summer of 1783, William made her own telescope, and she started to look for comets. And pretty soon she was discovering galaxies, star clusters, and she became the first woman to discover a comet. And over the next 11 years, she discovered another 7. But this is a lovely little cluster that she discovered with that telescope a couple of months after she got it. And it's called the Rose cluster because you can imagine petals around it. Now, those regulars will know we looked at globular clusters, a globular cluster last week, and these are enormous clusters of many hundreds of thousands of stars in a great ball. And these globular clusters hover round our Milky Way galaxy. And they're very, very old, often up to 12 or more billion years old. So they're nearly as old as our galaxy. But when we move inside the Milky Way, clusters are very different. They're called open clusters, and they're often only made up of hundreds or thousands of stars. And usually they're fairly young because they condense down from gas and dust and make a star cluster. And then usually the star cluster breaks up and the stars disperse into the interstellar medium. But Caroline's Rose cluster is totally different. It's enormously old. It's over 1.5 billion years old. And it doesn't seem to have dispersed. And it's so old that some of the stars have evolved and are starting to die because the bigger stars live fast and die young. And so we can see that some of the stars have an orange tinge. If you look closely, I can see several. David will point out to some of them, some of the red giants. And they've run out of their nuclear fuel and have started to swell up, just like our sun will. That's a nice one, yeah. Just as our sun will in about 5 billion years' time. So these open clusters we see all through the Milky Way, but not usually as old as this. They're very much younger, and later in the season we'll look at 2 nearby clusters called the Pleiades and the Hyades, which are much younger, and you can even see them with the naked eye, but we'll show you where to find them. So that's the Caroline's Rose cluster. Now we can carry on, and we hope to go back to Paul, who should have found the Vale Nebula. How are we doing, Paul? Deathly silence.
Hi, just give me 2 more minutes.
Okay.
I had to change the filter in the camera.
All right, I'll let you off. I didn't realise. Sorry,
No,
my
nor
mistake.
did I. I've done it now. I'm just going to pop the camera back in.
Yeah. But while you're doing that, the Vale Nebula was again another object discovered by William Herschel way back in 1784. And Paul will soon find it. But as I said, William Herschel made many hundreds of telescopes, and some of them were enormous. The largest one he called his 40-foot reflector. It was 40 foot long and had a mirror 48 inches in diameter. And the trouble with those mirrors in those days was they weren't made of glass or Pyrex or zero expansion material like they are now. They were made of speculum metal, which is a combination of tin and copper. And the trouble is they tarnished. So often William Herschel's telescopes usually had two mirrors, one being polished and one being in the telescope. And it took an enormous amount of skill to produce a parabola. It's easy to produce a curved mirror, a spherical curved mirror, but to produce a parabola is extremely difficult. And in those days, there was no way of testing. It was done more by using your skill. Wow, I can see it. This is the first time.
Enjoy it while it lasts. My battery failed.
Okay, go on then. Do it. Hit it with us again.
I can't. I'm going to have to get some power organised. This battery's run out.
Okay, no worries. I saw it briefly.
Electricity.
No worries. And as I was saying, I'll carry on waffling for a bit. As these mirrors took a lot of figuring, I said he worked up to 16 hours a day on making telescopes. And there's stories of Caroline Herschel, his sister, feeding him while he was polishing these mirrors. So, and then he would observe all night. He was absolutely obsessed. Amazing. Now, this, what you're going to see is once Paul sorted out his power supply, is called the Vale Nebula. You may have just caught a glimpse of a stringy bit in the sky. And this is a small part of a large ring in the sky. And this ring is about 6 times the diameter of the moon. And it's the remains of a supernova. It's known as the Cygnus Loop. Obviously, it's right near the constellation of Cygnus, the Swan. And this star went supernova probably about 10,000 years ago, and it's still expanding. And we know how fast it's moving because the Hubble Space Telescope has photographed it over an 18-year period and can actually see the debris expanding away from where the star was. And it's traveling, the stuff is expanding at 1.5 million kilometers an hour. Now, right in the middle should be a neutron star, and that's what's left of the star, which was probably about 12 times the mass of the sun when it went supernova. And so the bit that's left over is a neutron star, which is super dense material. But astronomers think they've found the remains of this neutron star, or the bit that's left over, but it's yet to be confirmed. Okay, happy? How's it going, Paul?
Right, that was my laptop battery that should have lasted 7 hours that died after 1 hour. So I've just got it on mains, and we're going to have to reboot and rejoin the Zoom session.
Do you want me to get back to you?
Yeah, get back to me after you've been to one of the other guys.
Okay, I'll see. Mick, have you found your other target?
I'm afraid I've tried, but I've not, because I'm having trouble with the focuser when it's standing vertical.
No worries.
Virtually overhead, so I'm afraid I can't show that.
Okay, never mind. We'll go over to David and see how he's getting on.
Hello.
Hiya. How's it going? Because the other two are having a bit of a nightmare.
Right. Here we go.
Here we go. Right. This is a galaxy. It's about 30 million light years away. And this was discovered again by William Herschel. And although some books say it was discovered by Caroline Herschel, but these books and websites are wrong. what it was a bit of a mix-up between brother and sister. They were both at the telescope, both at their own telescopes doing observings, and he was referring to this galaxy that he'd just found. Meanwhile, Caroline was referring to another small companion galaxy of the Andromeda galaxy that she'd just found. So the two of them found new galaxies on the very same night. And this is why there is some confusion and why these websites and books are wrong. This was the one that was discovered by William Herschel. That must have been a fun night. That must, when they were both found the same galaxy, only a few degrees away from each other. Anyway, it's called the Silver Sliver Galaxy, and it is roughly the same size as our galaxy and the same shape, but it's seen edge on, and you can see a galaxy is like two fried eggs back to back, and that band going right up the middle is dust and gas, because spiral galaxies do contain a lot of gas and dust, and David's just enlarging it here so we can see the obscuring material. And this galaxy was always reckoned to be very similar to our own galaxy, because especially if you look in the southern hemisphere at the central part of our galaxy, it looks exactly like this galaxy. But we found a few slight differences between this galaxy, the Silver Sliver, and our own galaxy. The Milky Way has, not too long ago, was found to have a bar going across the nucleus, and so it's known as a barred spiral. And the Silver Sliver Galaxy isn't a barred spiral, but the Hubble Space Telescope recently took some high resolution images of the dark obscuring stuff in the middle of the galaxy, where the nucleus is, where the bulge is. That's where a huge majority of old stars occur, where the yolks of the egg are, if you like. And when it looked at these, this dusty line going across this galaxy, it saw unusual filaments of dust radiating away from them. And they were informally known as dust bunnies, and extend hundreds of light years above and below this dust band. And the dust has likely been blown out by supernova explosions or intense star formation activity. And this star, in 1986, did have quite a bright supernova in it, but it was picked up by radio astronomers because it was very luminous in radio waves. Normally, as Belinda said in her talk, the stars are picked up, supernova explosions are picked up optically first, and then you look at them in other wavelengths. But this particular supernova was detected with radio waves and then was picked up later optically. And it's in a small group of galaxies, which is about a dozen other galaxies of various sizes. Okie doke. I think Paul should have his telescope up and running now.
I have indeed, Brian. Can you hear
Good.
me?
Yes, okay, we'll come and visit. We're going back to over, so we're flitting all around Cambridgeshire, and Paul should have the bit of the Vale Nebula.
Have you got that?
Yes, we can see a band of red and blue going diagonally down past that bright star.
Yeah,
I notice
that bright star is 61 Cygni, I think it is, or it's in the constellation of Cygnus.
Yeah.
And we're looking at the Western Veil.
The Western Veil, right? Yeah, he discovered. That was, as I said, was discovered by William Herschel, and this is just a small fragment of this supernova remnant. Other parts of it are not quite so clear, but it's absolutely huge. And as I said, it's 6 times the diameter of the moon, so no telescope can see it all. So a telescope generally has a field of view about the size of the moon, or less, about half a degree. So we have to look at it a bit at a time. But this is the brighter segment that was found by William Herschel, and the other fainter segments were discovered photographically, when you can make prolonged exposures and pick up faint detail. But William Herschel had incredibly sensitive eyes, and no wonder he picked up so many of these objects. You'll notice that it's slightly red, and to see it is often difficult to see red objects because your eyes aren't sensitive to red light. That's why you often see in observatories, astronomers work by red light. Then that doesn't destroy your night vision because your eyes aren't sensitive to it. But good old William Herschel, he managed to see this quite clearly. Paul, have you ever tried to look at this visually?
Yes, you can't see it at all with the telescope unless you put a special filter in the line of the eyepiece, which is called an oxygen 3 filter, that just filters out the greeny blue baked bean tin color. Yeah. That comes from is the blue that you can see in the image there. And then suddenly it kills off all of the background. The filter I was changing was I was trying to find my O3 filter. This is a different one. This is the CLS filter, the City Light Suppression filter, and that's why we're getting both the red and the blue through.
Oh,
it's
that's
quite
good.
Nice in color like that.
Yeah, this is
still
the first...
got a little bit of white over the background, and that's because there's a rather lot of light pollution around here, and the moon's come up.
Oh, yeah, never mind.
So,
but I must admit, this is the first time I've ever seen the Vale Nebula, and it's very good. But now I know how faint it is. I'm so impressed that William Herschel found it, because oxygen filters were not very common in 1784.
No.
So, yeah, he must have had incredible eyesight. Although, to be fair, the skies were much, much darker in those days. But there again, his telescopes, the mirrors weren't that reflective. Anyway, we've just got time to go back to David, who should have found his last object, which is another planetary nebula. David?
You must forgive me. I
can go and get the Dumbbell Nebula quite quickly.
Yes, I can. Yes, I can get the dumbbell quite quickly. Just give me a second.
Right.
Let's have a race.
Go on then. First one to get it. And we're coming to the end of our time, so it will be a short race, I hope.
Well, it'd be interesting to compare them.
Yeah.
I don't know if I can reach the dumbbell because of the trees.
Never mind. The Dumbbell Nebula is in Valpecula, and like I mentioned it before, the distances to these objects is very difficult to determine, and their size and their age. So it's just nice to look at them, because they're some of the most amazing things you can see. And the one we were going to look at was the Cat's Eye Nebula, but we've come across a problem. We'll probably have a go at that next week. But we'll carry on. I can hear lots of nearly there. Oh dear.
Let's see what we can see when the image refreshes. There it is.
Well done, you've won. Okay, this one, can we enlarge it a bit so we can see the white dwarf? Will it pick up the white dwarf in the middle? Again, you can see that this nebula is round in shape, and as I say, William Herschel named these planetary nebula mainly because they're round and absolutely nothing to do with planets.
I'm afraid I can't go any bigger, Brian, because I've got the telescope configured in its widest configuration. Okay. It's also not quite in focus, I think.
Okay, don't worry, we can
see. But let's go over to David.
We can see the colours beautifully, the reds on the outside and the blues and sort of greeny colours, hues inside, which indicate different colours. The reds are hydrogen, in which the nebula is expanding into the interstellar medium and exciting the hydrogen. That's why we see it as a sort of pinky colour. And the other colours are due to oxygen and nitrogen. Right, if we go over to David, let's see how he's found, if he's found the dumbbell.
And
here we come.
I've I've lost. There you are. No.
That's it. Talk to it. It will come.
Right. I need to share. Am I shared or not?
Not yet.
Not yet.
Right. It's a very noisy image.
Don't worry.
Can you see it?
Not yet. We haven't shared.
You're not
yet.
shared.
Ah, I beg your pardon. I didn't click the other button. Share screen. That one. Share.
Here we go.
That's it. Brilliant. Okay, it's a little bit grainy, but again, we can see the colours, and as he alters the exposure, because these images are live, and every so often the image is refreshed. How often is the image refreshed on this particular picture?
This is 30 seconds.
So every 30 seconds, the image is refreshed, because it needs that length of time to capture the delicate nature of this planetary nebula. But bang in the middle is the white dwarf. So any star under 8 solar masses, when it dies, will throw off the shell of material or something similar to what you see now, and all that's left of the star is a white dwarf, and these are enormously hot, often 80,000 degrees or more, and they're just what's left of the star, and they'll spend the rest of eternity cooling down. So that's all that's left of a star similar or bigger than the sun, but always under 8 solar masses. If anything bigger than 8 solar masses, it will go into a neutron star. and bigger than 25 masses, it goes into a black hole. So I think we've just about done it. We've run over by 5 minutes, but never mind, we had a little bit of trouble. But well done to our telescope crews. They did a cracking job despite some technical hiccups. So well done, and I hope you'll join us next week. Many thanks. And over to Paul. Have you got anything else left you want to wind up with?
No, thank you very much for your commentary, Brian, and thanks Mick and David for bailing us out. And I'm sorry I had the technical issues. I had my microphone batteries die, and then the laptop went. So it was I must charge them all up beforehand.
Oh, that's a good picture now. That's come out quite lovely.
Superb, isn't it? Yeah,
it's brilliant.
This is 60 seconds.
Right, that's good. So the longer you give the exposure, obviously, the more detail you'll see.
Yeah, collect more photons.
Yeah, but these are generally these planetary nebulae are just a few thousand light years away. They're not very far, but as I say, the distance cut isn't very well known. So hope to see you next week. Thanks very much.
Over to Matt.
Yes, wonderful. Thank you very much, guys. Fantastic stuff as always. I love the theme of William Herschel running through the whole thing. Yes, wonderful, and some wonderful images. Thank you to everyone at home. Hope you enjoyed both the lecture and the observing. And yes, we will see you next week.